trig to solve for angle measures as well as solving for side lengths. I explained solving for side lengths in a previous video, and now we'll look at finding angle measures using right triangle trig. One of the first things we need to know is if we've got a right triangle, and since the diagram does show a right angle, it is. Of course, we could check that by using the Pythagorean theorem as well, and 9 squared plus 40 squared will equal 41 squared. So we do have a right triangle. So we know we have a right triangle. We can pick really any of our trig ratios to set up an equation that we can then solve for a missing side. I'll go with tangent of angle A. So I'm going to focus on angle A, and I'm going to label my sides. Hypotenuse is always opposite the right angle. Opposite of angle A is over here. And adjacent leg to angle A is right here. One of the things I typically would think of if I'm really just learning trig is always label a hypotenuse first, because it's always opposite the right angle. That helps reduce the confusion with the adjacent leg, because some students will think that this here is adjacent to angle A, but it's not the adjacent leg, it's the hypotenuse. Okay, so I've got my sides labeled. The tangent of angle A, well, tangent in general is opposite over the adjacent leg. In that case, it's 40 over 9. So we have an equation here with really, we only have one variable. The only variable is the angle measure for A. Tangent is not a variable, it's a function that it has an input of an angle. Functions often have inverses. This function kind of has an inverse. This is something I'll leave to in-class discussion for you. It's a function that's got an inverse over a certain set of values. So the tangent of angle A is equal to 40 over 9, so we're going to apply that inverse function. And whatever we do to one side of an equation, we have to do to both. Alright, so we are applying the inverse tangent function of tangent of angle A and the inverse tangent of 40 over 49. It's kind of like multiplying both sides by 2. It's something that we're doing to both sides. Anytime you're working with equations, you kind of have to follow, or you do have to follow that rule. Alright, so when we do the inverse tangent of the tangent, we just get angle A. It's kind of like if you do multiplying by 2 and its inverse, dividing by 2, you would just be left with whatever number you started with. So the inverse of the tangent, inverse tangent of angle A is just angle A. And now I'll use my calculator to determine what the angle A would be. So the inverse tangent of 40 divided by 9. And again, make sure your calculator is in degree mode. Your calculator probably has degree and radian modes. And the angle A will be approximately equal to when you're doing your rounding, round to whatever angle measure your teacher specifies, 77.32 degrees. And I would want to check to make sure this seems reasonable. Definitely the largest angle is my right angle, and that's opposite of 41. 77.32 would have to be our second biggest angle, because we're only left with about 12 point something left, 12.68 left. So that would make sense that our smallest angle would be opposite of the 9, our second largest angle would be opposite of the 40, and the largest opposite of 41. So that helps me just kind of check to make sure that this answer is reasonable and probably then correct. It is correct. Alright, so that's using right triangle trig to solve for an angle measure. You can do pretty much the same thing using sine or cosine. If I wanted to find angle A using sine, my setup equation would be sine of angle A is equal to opposite over hypotenuse, 40 over 41. And then again, I would use sine inverse on both sides. Go to the calculator. expect the exact same answer. And it is 77.32 approximately. Same idea with cosine. Cosine would be cosine of angle A is equal to 9/41, and would again get the same value, 77.32. So we can use right triangle trig to solve for side lengths as shown in a different video, and right triangle trig to solve for angle measures as shown here.